Okay, section 4.5 is a discussion on rational values, specifically their graphs. So as you can see here, I have an example of what a rational function looks like. I think we've actually seen them before. It's just a fraction, but instead of numbers, there's a polynomial function for the numerator and also one for the denominator. So you can think of it like this. Up here we might have a bunch of terms, and down at the bottom a different polynomial function, or could be the same, with its terms all the way down to a constant term if there is one. So that's what they look like. We kind of looked at them before, but now we're going to go into detail. We're going to try and figure out how to sketch a graph of these things. Today, we're going to be looking specifically at asymptotes, how to figure out where they are so that that'll help us eventually to sketch the graph. And as you recall, back in section, I believe it was 3.2, you can go back and look. There was a discussion on asymptotes. Basically, they're a line where the graph can get closer and closer and closer to it, but could never touch it. So we'll see how that works here and how to find them. Okay, so the first thing we could notice, and it'll actually lead to asymptotes. If this is a fraction, the denominator can't be 0. So right off the bat, we know that the domain for one of these functions would be all real numbers except the zeros, the real zeros, or just the zeros in general, of the denominator, d of x. So if I find zeros here, they're out of the domain, because obviously they're not allowable numbers or values. Okay, also, since the function can't exist at those x values, if we do find a 0, then that means those are also vertical asymptotes. Now, we got to be careful here. You could have all kinds of zeros, but the problem for an asymptote is we got to plot a number on the x-axis, so that for vertical asymptotes, that would be all real zeros. So if we have any complex zeros, they don't count. So slight difference here. Okay, so just a real quick example. There's plenty in the book, but let's do one here. Let's suppose we have this rational function. It looks like this. X squared minus 4 over x squared minus 1. And what we'd like to do is define the domain and also lay out the asymptote so we get an idea of what this graph's going to do. Number one, we don't care what's on top. Ignore that. We're just looking at the bottom. And I'm trying to get zeros. So in other words, what x values gives a 0 for this function down here? Well, add 1, or better, this is a factorable. That's the difference of two squares right there. So that's going to be x plus 1 times x minus 1. This is the easiest way to do it. And then what are my zeros? Minus 1 and 1. So what does the domain look like? All real numbers except minus 1 and 1. If we're asked to write it that way, then we're done. If we need to put it in interval form, then what are we doing? We're starting at negative infinity. When we get to minus 1, we can't count that. Then we pick it up again right after minus 1, and we go to 1, but we can't count 1. Then we pick it up again right after 1, and we go on out. So there's the domain. These are both real roots, real numbers. So the asymptotes are at these points. So let's see what let's kind of get that started here. Okay, so at minus 1 and at 1, we have asymptotes. Like that, vertical asymptotes. Okay, and the curve's going to be somewhere in there. We need to look further here. Okay, next we want to see if there's any horizontal asymptotes. So that's a little bit trickier, but not too difficult. So for horizontal asymptotes, all we're looking at are the leading terms of the numerator and the denominator. And here for the numerator, we're using a to x to the nth degree, and for the bottom, just to keep things straight, we're using b times x to the m. So the degree for the denominator is m in this case. So here's a couple of rules. If the degree in the numerator, leading term, is less than the degree of the leading term in the denominator, then we have a horizontal asymptote. Horizontal asymptote at y equals 0. And what is y equals 0? That's the x-axis. So it would actually be the x-axis would be the asymptote. All right, what if n equals m? Same thing, we're going to have a horizontal asymptote, but this time it's going to be at y equals, and we need to look at the coefficients here. It's going to be the coefficient of the leading term on top divided by the bottom one. So it'll be that number. Okay, so let's look at g of x here. For g of x, if I compare the powers here, the degrees, they're equal. N equals 2, m equals 2. So that means we have an asymptote at y equals a over b. Well, it's pretty easy here. A is 1 and b is 1. So at y equals 1, which would be here, I have a horizontal asymptote. Okay, so one more thing. When it comes to vertical asymptotes, these values are not even in the domain, so the graph can never equal something on these lines, so it'll never touch or cross. However, with a horizontal asymptote, it's possible to get really close to it, but then cross it and get really close somewhere else. So it may or may not cross, and there's a test for that. What you want to do is, you got your v of x equals p of x over d of x. And the test is easy. For v of x, put in the asymptote value. In other words, if we had a value of y equals 0, then we would have 0 here. In our case, in a minute, we're going to try this test, and our asymptote is 1, so we would have a 1 here. So set the function equal to the asymptote, and then you have your regular polynomials here. And then what you want to do is solve for x. Two possibilities. You get a solution. If you get a solution, then the graph crosses the horizontal asymptote at x equals whatever the solution is. If you don't get a solution, and we'll see an example of that, no solution. In other words, that's going to be one of those deals where you get something like 5 equals -2. It can never be true, so it's a no solution. If no solution, no cross. It never crosses. Okay, so let's try ours real quick. For us, we had g of x equals this. We discovered that we have an asymptote at, and remember, g of x is really the y axis, right? That's the value of the function. So we're saying for ours, y equals 1, that would be like g of x equals 1. So put 1 in for g of x, and then solve this for x. So multiply both sides by this guy. And then we can subtract x squared from both sides, but look what's left here. -1 equals -4. That's no solution. That can never be true. So that means our graph, wherever it is, cannot cross the vertical axis. We're going to talk about actually sketching the graphs later. Basically, we'll pick test points and do other things to try and figure out which way it goes, but I'll just, for now, sketch this graph. It would look something like this if we figured everything out. So you'll have two pieces here that get closer and closer to these asymptotes, and then you'll have a piece in the middle that actually looks like this, but none of them can ever touch the horizontal asymptote in this case. Okay, let's try another one. Let's try this one. Okay. 3x over x squared plus 2. Let's take a look at the bottom. What are the zeros of this thing? Well, if I subtract 2 from both sides, because that won't factor. If I take the square root of both sides, I got a square root of a negative, so that's going to lead to minus I times the square root of 2 equals x. That's a complex root. And remember, it's plus or minus. I forgot to do that when you take the square root. So we're going to have plus or minus I times the square root of 2. Complex roots. So we have roots, but unfortunately they're not real. So we have no vertical asymptotes, okay? Again, the only way to have vertical asymptotes is we need real roots. So right now, our graph is wide open. So far it can be anything. What about a horizontal asymptote? Well, here n is 1, m is 2, so m is less than n, so we have a horizontal asymptote at y equals 0 or the x-axis. So here are our axes. That's actually also an asymptote, so maybe we could just make it a little darker. Okay, question is, our function will get closer and closer to this wherever it is, but can it cross it? Well, we need to do the test. V of x equals 0. That's the asymptote. And this is what v of x is right here. Solve this for x. I'm going to multiply both sides by this. Well, 0 times anything is 0. So if I divide both sides by 3, x equals 0. I think we can see that. So that means at x equals 0 on the asymptote, so here's the asymptote, at x equals 0, that would be the origin. Our graph is actually going to cross the asymptote at that point. Again, we're not doing graphing right now, we're just describing asymptotes and stuff. So the graph of this, if you actually see it, looks a lot like this. It actually crosses over the horizontal asymptote at the origin, and then it just gets closer and closer to the asymptote, but never quite touches it because it still is an asymptote. And that's how it works. Okay, so if you're looking here, all right, and you're paying attention, there's something missing here. All right, what happens if n is greater than m? If n is greater than m, then that leads to a whole nother class of asymptotes, which we're going to look at in part 2. And those asymptotes can look like angled lines. Might have a line going through here. They can even be curves. You could have a parabola as an asymptote, so your curve somehow would get close to it. So next time we'll figure out how to identify if you've got a line or a curve, and then furthermore, how do you get the equation of that asymptote so that you can sketch it in before you start trying to put your graph in there. Okay, so that's part 1.